All right, good morning. Where did my camera go? It disappeared. It's back. All right, how is everyone?
Not too bad. How about yourself?
Not too bad either, thanks.
Just been trying to get the ODP to work. The new
Good,
one.
good times. So I had the wrong ODP running by mistake. Somebody pointed that out in class last period, and so I fixed that. So the correct ODP is running. So if you tried before and you weren't getting credit, try again, because it might have been a problem on that end.
You're talking about for 409?
For 409, yeah, it was accidentally running 410 instead.
Yeah, it does show the correct one now.
Okay, good.
Yep.
All right, so any questions? All right, so let's talk about ingest and parsing. So these are terms that you'll hear me use a lot throughout this course and others. The general idea is you're running a program. Programs are more interesting if they're interacting with a user, right? So we don't just want a program that always does the same thing. We want it to somehow, get some information from a user and then do something in response to that. And so one way we do that is by, when we run the program, we put some arguments on the command line. For example, GCC doesn't always do the same thing. If you say GCC, f1.c, it compiles f1.c. If you say GCC odp409.c, it compiles odp409.c. So you're supplying information to your program on the command line, and that affects what it does. Or VI, right? You say VI and you put something on the command line, you put a file name, but then when VI is running, you're typing. And what you're typing changes what VI is doing. So those are our runtime inputs, right? So in general, when we're feeding information to a computer, there's sort of two steps we can think of from the point of view of the program. There's an ingest step, where the program is receiving information from a user, and then there's a parsing step, where the program is actually looking at what that input is and trying to understand what it means. So for example, when you open a book, right, the process of opening the page and having light, reflect on it, and the image goes into your eyes and focuses on your lens, right? That's an ingest process. That's taking in the visual patterns that are on a page of paper. But the parsing part is now, your brain looks at it and it takes those shapes and it translates them into letters, and it takes patterns of letters and changes them into words, and takes pattern of words and changes them into sentences and interprets a meaning from those, right? So it's almost like ingest and digest, right? But we call it parsing in computer science. So this is purely just taking in information. This is interpreting the information. And then typically there'd be another step, which is processing, where we do something about that information, right? But the main input piece is really, two chunks: ingest and parse. So for the ODPs that we've been doing, right, 408 and 409 today, the ingest is really just, the person running the program puts something on the command line. And once our program's running, we can say, you know, let's do something with argv bracket 1. So the ingest isn't really a separate thing there. And then the parsing is using sscanf, right? Because argv bracket 1 might be, you know, a set of letters that spell hello. It might be a set of letters that look like, you know, 23.5. So understanding what that set of characters means, that's what we do with sscanf. Okay, that's the parsing piece. And later today we'll talk about a different way to ingest, which is to use this function called fgets. And fgets will let us pull information in while a program's running, and then again we'll use sscanf to do the parsing. All right, so keep those in the back of your mind, and we'll refer back to them frequently. So let's look at ODP 408 and review what sscanf does for us. So example of sscanf, right? So here's the declaration of the main program. We use sscanf to say, hey, take that argument that the person's supplied on the command line, interpret it as a double, %lf, and save that corresponding double in a variable called x, which we've declared to be a double, right? So that's the parsing of this command line argument. And then for 408, right, we basically take the square root of that and we print it out with a printf with a %lf format. All right. So any questions so far on sscanf? Because we're going to do some more interesting things with this in a minute. All right. So while we're here, send me an attendance ping. Let me know that you're tuned in. And let's look at this question of detecting extra stuff, because with this ODP, right, if I run this ODP 408 and I put a command line argument like 25, it says, yeah, square root of 25 is 5, no problem. If I say, you know, S1 25, haha, this is fun, it still says, oh yeah, 25, that's a good number, here's the square root. All right, so for ODP 409, which we'll dig into in a little bit, we will be able to tell the person said, hey, they typed in a 25, but there was some extra stuff after this. And we want to differentiate this kind of input from that kind of input. And we'll come back to sscanf versus scanf when we start talking about fgets. And we'll see some specific examples in code. All right, so let's figure out how we can use sscanf to detect that there's extra stuff after our valid number. Because the way sscanf works is it's a scan, right? It starts at the beginning of a string, and it scans, it moves over character by character, and as it's moving, it's saying, hey, you know, could this 2 be part of a %lf, part of a double? Yep. Okay, let's keep scanning. What about this 5? Could that 5 be part of a double? Yup. Okay, let's keep scanning. What about this h? Could that be part of a double? Nope. Okay, so it stops and it takes the 2, 5, converts that to a double, stores the value in x, and returns a 1 saying, hey, I converted one thing. So scanf is doing the right thing, but it's not doing enough for us. We want to somehow detect that there's this extra stuff here. So we're gonna write some code. So let's write a program called extra. Alright, so I'm going to do my usual argc and argv. And I'm going to sscanf argv bracket 1.
Do you need a space after the char star?
You don't need one. You can put one in, you can put it before the star star, you can put it after the star star. I think you can even do something like this, and I think it'll still work. But usually I do it like this.
I never know when the spacing's gonna be picky.
Yeah, and spacing usually doesn't matter in C unless it becomes syntactically ambiguous. That's a kind of general rule, but yeah, it's a lot less picky than Bash. All right, so I'm going to put a note here. I'm going to. You really should check argc before using argv. All right, I'll actually make that uppercase. Say again.
Operating on the RV, not on the car.
Say that again, please.
The two stars, those are operating on the RV. Those are telling the RV something specific about the RV, not about the character.
So we'll have a separate conversation another day about this, but basically, you know, char is a character. Okay? char star is a pointer to a character. In C, when you want to make an array of blah, you make a pointer to blah. So if you want an array of ints, you make a pointer to an int. If you want an array of characters, you make a pointer to a character. So this is a pointer to a character. It's also an array of characters. But it's also what we call a string. So if we think of char star as meaning a string, what is char star star? Well, if this is a string, then this is a pointer to a string, which is also an array of strings. And that's what we really want to think of our argv as being. It's an array of strings. So argv bracket 0 is a string, a bunch of characters. Argv bracket 1 is a separate string, bunch of characters, and so on. But the way that ends up looking when you write it in C is, you know, char star star. So I don't know why I usually put the space after the first char. I think it's a mantra. It's just how I write char star star. But normally I would probably do something like char star and maybe star argv or something like that. But it's purely just style or personal taste. All right, so you really should check argc before using argv. If I don't do that, I am inviting seg faults, right? And we'll see seg faults when we're running this. But I'm going to live in seg fault land for today and not bother checking argc because I believe that when I run this program called extra, I'm always going to put something on the command line. And remember, if I say extra and I put anything on the command line, argc will be equal to 2. This will be the first thing, this will be the second thing. So these will be elements of this argv array, right? And argc will be equal to 2. But if I just say extra, argc would be equal to 1. This would be bracket 0, and bracket 1 would be, you know, an invitation to a seg fault. Alright, so I'm going to ignore my advice and not bother checking argc. So I'm going to scan argv bracket 1 as an integer. I'm going to store the result in num. And then let's take a look at what happened here. Let's just print out these values. Let's print out the value of our return from the sscanf call, and let's print out the value of num. did I call this thing? Extra. All right, so if I say extra 25, return equals 1, num equals 25. That's good. If I say extra 25, haha, returns equal to 1, num is equal to 25. Return is 1 because starting with 25 HA, it, tried to find an integer. Well, the 2 and the 5, those matched an integer, so it took those, converted them to num, and returned a 1, saying, hey, I converted one thing. So with this code, as I have it written, I cannot differentiate between this and this. But I can differentiate between those and this. Because if I just say extra haha, it tells me, hey, my return was equal to 0. Now, return is the number of things converted. If this succeeds, return must be equal to 1. If it fails, return will not be equal to 1. Right? So I could put in a check and say, is return equal to 1 or not? So let's do that. So if return equals 1, then this was good input. So I'll say good input, number equals 0. Otherwise, something is wrong with your input. And I'll go ahead and repeat what your input was. And so this will do a little cleaner job of parsing, right? So if return is 1, you got a good integer, I'll tell you what the number was. Otherwise, something was wrong with your input. And I'll remind you what the input was. And if you put in a good value, I'll go ahead and show you what the value was. So extra 2, that's good input. Extra x, something's wrong with your input x. But still, there's a problem with, if I say extra 2x, it says good input. All right, so how do we pick up this extra stuff? We're going to change our scanf pattern. So we're going to do the following. I'm going to make a character array. I'm just going to call it extra. And when I do my scan, I'm going to say, let's pick up an integer followed by anything else. Oh, wrong place. When I do my scan, I'll say, let's pick up an integer followed by anything else. And so we'll scan for an int, which will get saved in num, and we'll scan for a string, a collection of characters, which will get stored in extra. And with that one change, this is going to work a lot better. So extra 23, that works great. Extra 23, haha, tells me there's something wrong.
Is that because there's only those 2 data types if you scan one character at a time? Because you can't have floats and long floats and stuff if it's only scanning one character.
Well, effectively, yeah. So let's say my input is 23, and I'm scanning with a %d, %s. All right. So scan starts at the beginning of the string, and it says, hey, I should be looking for a %d. So here's a 2. Is that part of an integer? Yeah. How about a 3? Yeah, that's part of an integer too. How about an h? No. Okay, so it stops here. It takes these 2, and it associates these with the %d. And I've got my variables here. So we'll take that 23 and it'll put it into this first argument, num. And now it's going to continue. Hey, I've got more things to scan for. I'm looking for a string. So it'll say, could h be part of a string? Yeah. Could a be part of a string? Yeah. There's the end of it. Okay, so it'll take this HA, it'll associate it with this %S, and it'll store that in this thing called extra. And since it's stored two things, it'll return a 2. Now, if my input is something like just 23, right, the scanner will say, here's a 2, that's an int, here's a 3, that's an int. That's the end of my input. Okay, 2, 3 gets associated with %d. It'll store that in the num. There's nothing left here. I'm at the end of my string, so here the return value will be 1. So by looking at this value of return, if it's exactly 1, I know that my thing I passed to scanf had an integer and nothing else. If it's 2, there was some extra stuff. If it's anything else, this wasn't an integer at all. So I can make my code a little more nuanced. And I can do something like this. If return is equal to 1, then it's good input. Else, if the return's equal to 2,
Wait, does it count periods as still possibly being a part of that the number scan?
well, let's find out.
Because I would assume that'd be a string character.
So if the return's equal to 2, meaning that it matched both an integer and some extra stuff, I'll print a different message. I'll say, you know, num is a valid integer, but there is extra stuff, colon, and I'll show you what the extra stuff was. Otherwise, if it's not 1 and it's not 2, then it didn't even find an integer, and so I'll say there's something wrong with your input. So let's see what this does. So extra 23, that's good input. Extra 23, haha. Right, 23 is a valid int, but there's extra stuff, haha. And extra hee is something wrong with your input. So what about 23 period? Well, 23 is a valid int, but there's extra stuff. Period is not part of an integer. If I do extra minus 23, that's perfectly fine. If I do extra minus 23 minus 3, the minus 3 is extra stuff. So if you wanted to write your own program, starting from scratch to detect a valid integer, it's fairly complex, right? You need to be able to you know, deal with minus signs in the beginning, and so on and so forth. sscanf does this for us, right? So if I say extra plus 23, 23, you know, plus 23 is a valid integer. Plus 23 is not.
So 2.3 would give you 2, and then say the extra stuff is 0.3.
Yep. 2 is a good integer, 0.3 is extra stuff.
But if you change that %d to a %lf, would it count the 0.3?
So if we decide to do doubles, so let's change that to an LF. Let's change this to an LF. So if I do extra 2.3, it says good input, because that entire input, 2.3, matched the pattern %LF. But if I do 2.3 point, it says, hey, 2.3 looks good, but there's this extra thing at the end, this period.
That's because it reserves that 8-bit chunk. As it scans through, it knows how to handle that.
What 8-bit chunk?
You always figure a double or an LF is taking up 8 bits, which is why it shows the 7 characters. But I just was kind of trying to reason
So-
why it knew how to scan. But
So %lf is looking for a double, which is actually 64 bits, 8 bytes, and the number of characters could be could be more. I'm only printing it out. When you do %lf to print, it only prints a certain number of characters, but I could print more of these if I wanted. But the real action here is how scanf is working. So if I say 2.3 and I've got a %lf %s, then same thing, the 2 and the point and the 3, those all match the %lf. And if I had a 1 over here, that would match, but then if I have an x, that doesn't match. So this is the whole piece that goes with the %lf, and then it continues and it finds this extra stuff, and that goes with the %s. So this would go into the number, this would go into the extra.
So I noticed that on that other one where you put some letters before the number, it looked like it just threw them away because it was like, hey, I'm looking for a double first, and then I'll look for an extra.
So it's starting at the beginning of the string. It's looking for characters that match a %lf. The first thing it sees is the letter y. That's not part of a valid double number. And so it gives up at that point.
So it knows how to parse different types of data, or like different data types under the hood.
Yep.
scanf like function, but you're defining the order period.
Yes, exactly. And you always want to use, sscanf when you're trying to parse things. Don't try to do it yourself. Don't use A to I, right? That works in 121, but it doesn't tell you if something went wrong. And don't try to parse it yourself. Don't start looking for digits and minus signs and stuff like that. sscanf already exists. Somebody wrote that for you, and it does all the odd special cases, right? So I can do extra, 2.3 exponent 45, exponent 5, right? And it understands scientific notation.
So back in your code with the return line, how come the extra it doesn't have the ampersand? I was thinking it would need that.
Well, that's a deep question and definitely a topic for another day, and we will talk about it. But the short answer is, when I declare an array of characters, this is actually a pointer to a character. Which means that what I'm passing here is a pointer, right? But num is not a pointer. Num is just a double. I need to turn it into a pointer by putting the ampersand in front.
Right. I know that now.
So that's the short answer.
I already defined it as something, and therefore it already has it built in.
Yeah, so for any function to pass back, to change the value of an argument, you have to pass an address. And for a double, we have to say, don't pass the value, pass the double by putting an ampersand. But extra is actually the address of the first character of this string. That's how strings work. But another day we will have to talk about pointers and arrays and strings and how those all relate to each other. And that will also take us into why we have a car star star up here instead of just a car star. And yeah, someone probably did their thesis making sscanf. It's not an easy thing. You can download the source code for it and see what it looks like. And most languages have something like this. In Java, you could look at the scanner object or the scanner class, and it's huge, but it's usually built on top of other things. But to try to do that from scratch is usually not going to be successful. Integers you might be able to do yourself, but there's no need, right? We've got sscanf. So this is the way in this course, and maybe beyond this course, if you want to really make sure that a command line argument is exactly what you're looking for, right? You can always use this trick. Scan it with, the format specifier for what you want, but if you want to know if there's anything beyond that, just do a %s, save that in an extra, and if the return value says, hey, I not only scan this, but I also scan this, in this case if return is 2, you're guaranteed, hey, there was something extra after my input. And you might just go with, you know, the thing that you input already, or you might just print an error message and give up, or whatever. And this basically takes us to ODP 409. So let's take a look at 409. So the behavior of your function, if everything is correct, is exactly the same as 408. You run your program and you put in a value and it prints out the square root. The difference is, in this case, some of the tests will use illegal values. I might run this without putting an argument at all. I might run it with something that's not a double. I might give it a negative number, which you can't take the square root of. So you're going to do error checking. Okay, what we call full error checking. All right, so there's three things you need to check for. The first is make sure that you have exactly one command line argument. If you try to run this without an argument, it should say error. If you try to run it with two command line arguments, it should say error. And this is the first thing you check. Check how many arguments you have. If you have exactly one argument, argc will be equal to 2. So that's your first thing, check argc. If argc is not 2, print out an error with a new line and just exit. But if you get past that if statement in your code, now you want to see if that one argument is in fact a double. So use sscanf and scan it with a %lf and do the %s trick to grab extra stuff and make sure the return from sscanf is 1. Okay, if it is not, then you print out invalid and you exit. So if I do S123X, it just says invalid. If I say S1X23, it says invalid. If I say S1, 23.4.5, it says invalid. So that's the second thing you're checking for. First, make sure there's exactly one argument. If there is, make sure it's a valid double. And that it's exactly a valid double with no extra stuff. Okay, if you get through those two checks, you have one more condition to check. Make sure that this valid double is not negative. If it is, print negative. So if I say S1 negative 9, I put in one argument, that's good. It was a valid double, that's good, but it's negative. So I print the word negative. Right? If it's negative 9.2x, that's invalid. Don't check to see if it's negative because it's not even a valid input. So these things are sequential and the order of these are critical, and this is always going to be the case pretty much any time that we're doing parsing. There's going to be usually a series of things we want to check and the order will be critical. If I check to see if I can scan this thing before I check to see if argc is at least 2, I'm probably going to segfault. Right? So first make sure there's an argument. If there is, make sure it's a double. If there is, make sure it's not negative. And it doesn't make sense to do those in any other order. Right? Don't check your thing to see if it's less than 0 unless you know that it's a number. So check this first, and then check that, and then see if it's negative. If you survive all three of those checks, you've got an argument, it's exactly a double, and it's not negative, then do your ODP 408, calculate the square root, and print out its value. Does that make sense? And so I put a sample program under /temp that you can run to sort of verify what your program should do. And when you run this, it will give you extra output. So your program should not print these messages. It should not print this message. Your program should only produce one line of output. In this case, this number, right? But the things in parentheses are telling you what the program's doing, right? If a single non-negative argument is given, do what ODP 408 does, which prints that out. If I do 23x, it prints out invalid. And what's happening here is that it detected an argument, but it wasn't a number. If I do 23, that's, or ODP, that stuff, right? An argument was detected, but it wasn't a number. If I don't specify an argument, it didn't detect the correct number of arguments. If I do 1 and 2, that's not the correct number of arguments. If I do -1, it's a negative argument, so I print the word negative, neg. So you can double check, right, if you don't remember from this part of lecture, you can double check what this program should do by running s1pub from temp. All right, questions about that? All right, so let's talk about the other way that we can specify input to a program, the other version of ingesting, which is when your program is running, you can specify input. And we typically do this using a function like fgets. And so let's write some code to explore this. Alright, so I'm going to make a big character array that can hold 120 characters. And I'm going to do the following. I'm going to say fgets. Fgets takes 3 arguments. The first argument is the name of where you want the input to be stored. That's got to be a character array. So I'm going to say temp. The second argument is how many characters can be stored in that array. Well, I declared temp to be 120, so I can say 120. And the third argument is where you want to input from. And for us right now, we're going to read from something called standard in. That's the keyboard, or if we direct input from a file or a pipe, it's whatever, you know, we've directed in. But it's standard in, typically our keyboard. All right, and then I'm going to just see what temp is equal to. All right, and I'm going to do a trick here. When I print this out, I'm going to put delimiters before and after this. So that if there's spaces in this variable temp, I'll see them because I'll see spaces between the starting and ending angle bracket here. All right, so pretty simple test program here just to play around with this fgets function. And I've called this fgets. So let's go ahead and run this. So if I say hello, it says temp equals hello, and this closing angle bracket came out on the next line. So I typed in 5 letters HELLO, but it looks like my string, my character array, contains an HELLO and something that caused my output to go down to a new line. Well, guess what? That's a new line character. And so if you do a manual page on fgets, it says reads in at most 1 less than size characters from the stream, stores them in a buffer pointed to by S. Reading stops after an end of file or a new line. If a new line is read, it is stored into the buffer. So this is the first good thing to know. There's always a new line at the end of our input. If you're reading from the keyboard and you hit an enter, that enter basically generates a \n character 10 or a new line, and that's part of your input buffer. It also says a terminating null byte is also stored after the last character. So remember, strings are not a part of the C language. And we pretend that we have strings by using arrays of characters. But when I say something like quote ABC, what I'm really doing is I'm saying somewhere in the memory of the machine, let's find some location and store the letter A. And in the next location, let's store the letter B. And in the next location, let's store the letter C. And then in the following location, let's store a character null. right? So a \0. And this string, quote ABC, actually refers to the location in memory where that A is stored. So this is an array. If it was an array of integers, we'd have a bunch of numbers. It's an array of characters. But since arrays in C don't have a predefined length, even if we say, you know, integer x bracket 10, there's nothing in your memory that tells you that there's only 10 integers in this array. It's not part of the language. So for strings, we need to know where this string ends. So the convention is we put this null terminator, this special character, after the last character of the string. And pretty much every string you deal with in C, you're going to have a null terminator at the end. So fgets, since it's creating a string for us, we'll put that null terminator into the buffer. So when we say fgets 120 characters into temp, temp will contain everything that we typed in, followed by a new line, followed by a null terminator. And this can be interesting because if I say, let's make temp 3 characters, and so I'll tell fgets, you know, I can read in 3 characters. And I type in hello world, my temp is only equal to HE. Right, so why is that? Well, my call to fgets, I said I only have 3 spots available inside temp. So it read the first character H and it stored that in the first spot of temp. It read the second character E, stored that in the second spot of temp. And then it said, oh wait, I need 1 space to store a null terminator, I'm going to stop right here. And so it really only read the first 2 characters of input, stored those, and then stored a null terminator at the end. And there's no new line in this case. The new line would have happened after it stored HELLOWORLD, and then a new line. So in order to store that, I'd need my character array to be big enough to hold at least 12 things. We can avoid most of this complexity by just making our character strings big. So most of my code, I just make strings 120. Right, and we're not going to run into this. But if you're trying to get, you know, a single character from the user, like, do you want the user or computer to go first? Type a U or a C. And if I try to do an fgets with a length of 1, it's not going to work. Because I can't store a character in that. And if I try to make it 2, it'll probably work. But if I put in more than 2, it may not. Just make your arrays big. Memory is cheap. Alright, so yeah, let's talk about gets, since somebody asked. And yeah, the short answer is it can cause a buffer overflow. But let's see what this means. So it's instructive to look at the manual page for gets. And under description, it says, never use this function. Right? And the shortcoming of gets is you run gets with a character array. But, you know, arrays don't have predefined lengths. So if I just give it the name of this array, gets has no way of knowing how much stuff it's allowed to put into that array. And so, you know, if I make this 3 characters long, and I just do something like gets temp, I'll compile it. It will give me a warning, right, saying, hey, you know, did you mean fgets? And it will tell me gets is dangerous and should not be used, but it'll still compile. And so if I run this, I can say hi, and temp is equal to hi. I can say hello, and temp is equal to, oops, stack smashing detected. Right? So simply by typing in different things, I can cause this program to crash because it's compiled with these safeguards that detect that I was putting in more stuff than I allocated memory for. But if I don't have those safeguards set up, you could type in, you know, 1,000 characters here, and where would those characters get stored? Well, they get stored in memory after wherever this variable temp is pointing. So on my picture, you know, if I type in more than a few characters, they just keep getting stored in consecutive memory locations. Now, if this program is running on the web and I'm saying, you know, tell me your name, and the person types in their name, and my C program, you know, saves it in temp, and I say, hello, you know, temp, nice to meet you, right? But somebody who's malicious, you know, it says, hey, tell me your name, and I say gets temp, they could start sending in, you know, thousands of characters chosen in such a way that as they start filling in memory locations, it eventually changes, you know, a flag somewhere saying perhaps, you know, you logged in as an administrator. And then, you know, the system would come back and say, oh, welcome, administrator. What would you like to do? And I'd say, transfer all the money to my account in Switzerland. And, you know, bingo, hack. So gets is inherently prone to buffer overrun attacks. And if you're being malicious, right, that's a really bad thing. If you're not being malicious, you can still get into trouble, you know, by having an error in your code that fgets would basically save you from. And the real difference is with fgets, right, it says it reads in at most one less than size characters. So this argument right here is saying what's the maximum number of characters that I want to put into here. And as long as you're consistent, as long as you say, you know, if this can hold 120 characters, you tell fgets you can read in at most 120, you won't have that buffer overrun problem. So that's a quick rundown on gets and fgets. And chances are, if you're in a job interview and you use fgets, you've lost the job, unless they're looking for a hacker. But you know, it's not like, you know, I wrote gets here, my machine is being hacked right now as we speak, right? There's nothing inherently dangerous about using gets, right? This is heresy. If I posted this on Stack Overflow, I would get, like, you know, flamed. But I mean, you know, having this gets call and running this program does not expose my machine to evil hackers, right, somewhere on the planet. It's a program that I'm running, and if I type in more input than I specified, I'm going to get a seg fault, right, or stack smashing or something. But it's considered to be, you know, so easy to, I guess, accidentally use this in your code, and it's been so hard dealing with legacy code that has this, that the general mantra now is never use gets, right? And so, you know, a hiring manager, for example, would probably like spit out their soda if they saw you write gets on a whiteboard. So yeah, just avoid this. All right. Yeah, so yeah, you could type in hex codes and get good stuff. All right, so any questions on that stuff? We're going to say a lot more about fgets tomorrow. We'll dig into more details of using this. So send me an attendance ping. Let me know you're still here. I'll fix this up so that the deities don't get upset at me. Tomorrow I want to play around more with fgets and look at how we use fgets and sscanf together and why just using scanf is a really bad idea. Okay, so we'll talk about that, and then we'll talk about PA2, which will be our C version of the stick program. So we'll go through that in detail. Classes, there's no classes on Friday. It's a faculty work day, so tomorrow we'll go through enough of PA2 so you can get started on that for the long weekend if you like. All right, thanks. Have a good one. I will see you next time.